do a little bit of lecture and then we'll take a break. So epidemiology, you know, it's part of public health. We're looking at the distribution of disease in populations. Our goal is to try and find risk factors that influence the distribution. And then we take whatever we learn and apply it to public health and hopefully get people to do change in their behavior that will help improve their overall health. So if you look at this schema, what kind of a trial is this? Yes. Right, it's a cohort study, and what's the giveaway? It's this non-randomized. You're starting with the population, they choose their behavior to be exposed or not, and then you follow them for disease. So this is a cohort study, observational type study. Whereas this here is what kind of a trial? Right, a randomized controlled trial, and it's experimental design because you are randomly assigning them to some different variables, whether it's a low-fat diet or a high-carb diet, whether it's, you know, a new treatment, an old treatment, whatever you're doing, you are assigning them, you are in control of the experiment. So there are different types of studies. We've gone over them. I expect you to know the different study designs: cohort, case control, cross-sectional, randomized controlled trials, ecologic studies. The units of analysis, we talked about how they can be individual or a group. For the most part, they're individual. Your measures of association, relative risk, what studies would you use that for? Cohort and randomized control and odds ratio, what would you use that for? Case control study. We can calculate incidence rates only in those studies where we're going forward in time, the cohort and the randomized controlled trial. You can do a rate ratio, a relative risk, or an odds ratio. And then what we're going to talk about today is the calculation of attributable risk or attributable risk percent. We talked about that if we're talking about incidence rate, the defining characteristic here is the word new, that there were 7 new cases of prostate cancer. And you give it per population at risk. So in this example, it was per 1,000 men over age 65, and then over a time period, and in this example, it was during 2008. Prevalence. Is prevalence a measure of risk? No, right. I saw some shaking of heads. You guys are really quiet today. So it is not a measure of risk, but it is a measure that's important. When we're planning public health, when we're determining the burden of disease, we need to know how much disease is there out there in the community. So this could be 14 men per 1,000 had prostate cancer when we asked them in 2008. We don't care when they got it. They're not new cases, but that's how many men had the disease. And remember that if you have a change in the definition of how you define disease, it's going to change the prevalence. So whereas you might have said that systolic blood pressure over 160 was hypertension a while ago, then they moved it down to 140. That was the new definition. So if I was talking about the prevalence of hypertension, if I used the old definition, it would only be the people in this tail. Whereas if I use the new definition, it's everyone from here that falls under. So a change in the definition can change your prevalence because you're going to move that line along the axis, and more people might end up having the disease depending on if you make it stricter or a more loose definition. Do you understand that? Okay. Yes?
So for prevalence, the change in definition will change your prevalence and changing the lifespan of someone with, say, diabetes will also change your prevalence. Is there anything else?
So the two main things are going to be adding new cases, so that could be from a change in the definition or just there's more risk factors or, you know, anything. So it's, you know, when you have more disease existing at any given time, and then also a change in the duration. And we're going to go through that in a couple of minutes, like now. So in a steady state, there's no change. If there's no change in the rates of disease that you expect, there's no migration of people in and out of your community. In general, we would think that prevalence is going to equal incidence times duration of disease. And again, I said, think of this qualitatively. I want you to say, okay, duration of disease goes up. What's going to happen to prevalence? It goes up, right? So that's how I want you to think of this example. So why is the prevalence of osteoarthritis in the United States really high? Yes? They live longer with the disease. So they have a long duration. They get osteoarthritis and then they go on for many years with it. Why is the prevalence of ovarian cancer low? Yeah.
They have a poor prognosis and people are dying.
Right, there's a poor prognosis, they die, and so they're not adding, to the duration part of that. So here is looking at the relationship among incidence, prevalence, and duration of disease for asthma in the United States. So they have it broken down by different ages. So if we look at people aged 0 to 5 years of age, the annual incidence is 6 per thousand, the prevalence is 29 per thousand, and the average duration is about 4.8 years. So again, it's just this relationship between these three variables I want you to be comfortable with. This is the rates of atherosclerotic heart disease per 10,000 population by age and sex in Framingham, Massachusetts. So here we have the rates at the initial exam and the mean annual incidence in men on this side and in women on this side. So if I ask you, in what age group is the relative risk of developing heart disease in men as compared to women the lowest? So your exposure here is male. What are the numbers that you're going to use? It's a relative risk. So which are you going to use? Which column? Okay, so I want you to say in which of these age groups, which are listed here, which of these 4 age groups is the relative risk of developing heart disease in men versus women, so the exposure is really men, or maleness, the lowest. So what do you want to use? What is this column giving me here? Prevalence, right? It's the rates at the initial exam. It's not incidence. What is this giving me? Incidence. This is prevalence, this is incidence. So if you wanted to do a relative risk, what numbers come into a relative risk? Incidence or prevalence? Incidence. So what would you divide? So let's take the oldest category here, 55 to 62. What numbers are going to be in your equation? 209.1 divided by what? Right, divided by this, and that equals 1.8. So if you did this for all 4 of these, but if you just look at it, you can kind of see that's the smallest difference between these two. This is like about 4-fold, this is about 20-fold, this one. So you can see this one, it being about 2-fold, it's 1.8, is going to be the lowest relative risk. Is that clear to everybody? So relative risk, you do incidence, you do the ratio of them, and that gives you an idea of how much of a risk it is to be a male and if it varies age by age. And at the oldest age, there's less of a difference. Why are the number of cases here so much higher than they are here? So why is 76.7 so much higher than 19.4? Yes? Right, because what is this number really? Right, it's prevalence, so they could have had a duration of disease for a long time, whereas this is the incidence, so that's why it's smaller. So we also might look at the annual mortality rate. It's the number of deaths in a year divided by the number of people in the population at the mid-year. And again, most of these things that we're dealing with are so small that we usually do it times 1,000, just so that we get a whole number and we're not talking about 0.06 people or, a non-real number. Case fatality rate is measuring the total number of deaths from a disease divided by the number of people with that disease. So if we had 1,000 men with prostate cancer and there were 10 deaths, what would it be? Yeah. Right. So do you understand? It's just simple. Just know which numbers to use in which scenarios. Now, what kind of a study is this? Right, it's a case control. It's kind of easy. It's got the word case down here, control down here. It's like 4 o'clock. I know it's a tough time of day, but we're going to get through this, all right? So here's looking at it a different way. So you have your cases. They have a cardiac arrest. You have your controls, no cardiac arrest. I didn't write case and control on here. You had to figure that out. So we're hoping that we're getting all of the cases of, cardiac arrest and a random sample of the people without cardiac arrest. We talked about sometimes how we match on things. In this case, they're matching on age, sex, marital status, and urban or suburban area that they live in. And part of that is because the hypothesis here is that prior exercise might influence whether or not someone gets an MI. So you get these people from the population, and then you ask about their prior exercise. Did they exercise or were they inactive? So everyone clear on what we're doing here? Then when we get all of our numbers, we have people with disease that were either exposed or not exposed. These are our cases with or without exposure, our controls with or without exposure. You drop them into the fourfold table. So you start with disease or not, ask about prior exposure. Usually you want to ask about this before they got the disease, put them in the fourfold table, and what do we calculate with this? An odds ratio. And what would the formula be? Do you want? Yes. That would be for incidence. So here we're looking at the odds ratio. So this is what we do. It's AD over BC. Okay, so you should all know how to calculate odds ratio. So this is, if you have an exposure that's associated with the disease, we expect that the proportion of cases exposed would be greater than the proportion of controls who were exposed. And that we calculate by this cross products here. And note that here we have disease on the top, here we have exposure on the top. Most of that does not matter. What really matters is that you have your two positive things up here, so that the disease positive, exposure positive is here, and then everything else will fall into place. Yes?
I thought she said A over C divided by B over D, which would be AD over BC when you cross multiply.
It would be, but I didn't want to confuse people. I mean, just think of this as the cross products. There is, the whole way we get to this is we start out with what you said, it wasn't really wrong, but then we say this number is so small, we're going to get rid of it and turn it into this equation. But for the purposes of making it easy for you for the exam, you should just think, odds ratio, how do I calculate it? Right. So that's just to make it a little bit easier. But you are right, mathematically, you were not wrong. So I'm sorry. Okay. So you can look at the calculations of the people that were, the proportions that were exposed in a case control study. So the cases you have here, you have controls here, whether or not they were exposed, yes exposed, no exposed. And then you can say what proportion were exposed, what proportion were unexposed. And then when we do it the easier way, we just do the AD over BC. So if we had an example here where we were looking at coronary heart disease, we had the cases, we had the controls, we asked them in the past, did you smoke or did you not smoke? Put everything into the table and you get AD over BC. And here you get a odds ratio of 1.62. So can someone tell me in words what this means? You all have to know by next week, so someone should just give it a chance. Yeah, you can go.
For any given person, that person has a 62% higher chance of getting the disease in question than the next person.
So that's how people sometimes interpret the odds ratio. But remember here, you can really talk about how likely they were to have smoked. So you're saying the cases were 1.62 times more likely to have smoked than the controls.
Yes.
Right? So it's a fine distinction because otherwise you're talking about risk of disease. And this is a case control study, and we really shouldn't use that as much.
Okay.
Does that make sense to everybody? So the cases in this scenario were 1.62 times more likely than the controls to have smoked. So because you're choosing a number of cases, you're choosing a number of controls, you really have no idea in the general population what proportion of them are going to get diseased in the future. You just chose them, and so that's why you can't really do the proportion, you know, how many, the incidence of the disease, or why you shouldn't use words like risk. All right, so remember, when a disease is rare, the odds ratio is in fact a good estimate of the relative risk. So in this example, you had only 300 out of 20,000 people got disease. So that's rare. Like, you know, people always ask me, well, what's rare? Well, you know, things like cancer are rare and things like this are rare. You know, it's not like a 50-50 chance of getting disease. It's only 300 out of 20,000. So if we calculated the relative risk, which is the number who developed disease in the exposed divided by all exposed divided by number of people who got disease in the non-exposed divided by all non-exposed, we get a relative risk of 2. If we do the odds ratio of the AD over BC, we get almost the same exact thing with the AD over BC. And that is because this is a rare disease. Now we'll flip to an example where it is not a rare disease. So in this case, you have 75 out of 200 people getting the disease. So that is not rare. You know, you almost could flip a coin and get the disease. So in this case, the relative risk calculated the same way, the number exposed who got disease divided by all who were exposed, number not exposed, 25 divided by all not exposed, 100, you put that into a ratio, it's 2. Now when we do AD over BC, we get 3. So they are no longer equal because the disease is not rare. So that is a concept that you should know. So interpretation of an odds ratio, 1, no association. If there's statistical significance, an odds ratio of 2 suggests that the cases were twice as likely as the controls to have been exposed. Whereas an odds ratio less than 1 says that it's a protective factor. Someone have a hand up? So here's a sample calculation. This is a case control study. They thought that chili pepper consumption was related to gastric cancer, so they did a case control study in Mexico City. When they did it, these are the calculations. So these are the gastric cancer cases. You had controls. You asked whether they eat chili peppers, and so that's the exposure yes, and this is the exposure no. So the odds ratio here, AD, so it's AD over BC, is going to equal 5.95. So can someone tell me now how you would interpret this? What would be the words to describe this? Yeah, in the middle. Right, so if you are a gastric cancer case, you're almost 6 times more likely to have eaten chili peppers in the past than if you are not. So an odds ratio, is a good approximation of risk when the controls are representative of the target population. In other words, there's no bias in your control. You have a good control group. When the cases are representative of all cases, and when the frequency of the disease is small or the disease is rare. So those are the scenarios where sometimes we say an odds ratio would approximate a relative risk. So now I'm going to teach you something new, and then we'll take a break. So this is matched pairs analysis. We talked about sometimes we're going to match our cases and controls, but we never really talked about, well, what happens when you do it. So we can do a matched pairs case control study. The table setup is different. So notice here you have the controls up here, you have the cases here, and each one is either exposed or not exposed. So here A represents where both the controls and the cases were exposed. And then D means that both the cases and the controls were not exposed. Those are concordant pairs. We don't care about those in a matched pairs analysis. What we care about is what we call discordant pairs. It means one group was not exposed, the other was exposed, or here the controls were exposed, the cases were not exposed. those are discordant. It means that the pairs, each one of these inside C is like a pair of people, and you have one that's exposed and one that's not. That means discordant. So when you do an odds ratio for matched pairs, you don't care about A or D, you get rid of them, and the formula is simply B divided by C. Now I'm going to go through an example, and hopefully it will be a little bit more clear. So this is an example of 12 pairs. So you have a pair of a person with uterine cancer, a case, and a control without uterine cancer, and you asked about whether or not they used estrogen in the past. So you ask about this, and you have, in this case one, you have an estrogen user case and an estrogen non-user control. So remember this, and we're going to go to here. So we want to know, what is the estimated relative risk of cancer when analyzing this study as a matched pairs study? So we're going to go forward and do that. So we have our fourfold table. So remember, it's the controls across the top, and they're either exposed or not exposed. Cases are either exposed or not exposed. And that's how we set this up. So if you go back to the data, you can see how this would fill in. That you would have two people that were estrogen users in both the cases and the controls. So if we go back to this, you want to see how many places was it where this was an estrogen user and this was. So we have pair 3, we have pair 4, and then there's no other ones, right? So there were only 2 people where both were estrogen users, and that's how you go about counting these to put them into the table. And remember, the ones that we really care about are the discordant pairs. So the ones where the case was exposed, they were an estrogen user, and the controls were not an estrogen user. And there were 6 examples of pairs where that was the case. As I said, we don't care about this where they're both exposed. We don't care about this where they're both not exposed, but we care about this, and we care about this. And what did I say was the formula for a matched pairs odds ratio? B over C, right? So that would be, in this case, 3, 6 divided by 2. So this should make sense to you, but you know, you might want to go back and forth between this when you go home and just make sure that it's all clear to you. So then what we want to do is we want to consider unmatching them. And so now you have your uterine cases on the top, your controls, and then whether or not they used estrogen is here. So the number of uterine cancer cases that used estrogen was 8. And we can go back to that table and calculate each of these different cases. The controls without any estrogen exposure was also 8. So we could put this now into a formula. This is not a matched study, so what is our odds ratio formula? AD over BC. It's the same as it always was. So in this case, it's going to be 8 times 8 divided by 4 times 4, or 64 divided by 16, and that equals 4. Does everyone understand where that came from? Just go back again and make sure you're comfortable with where the numbers come from and how you would do this. And I have 2 more examples of matched case control studies, and then we'll take a break. I'm sorry. Yes?
So, Dr. Nieves, if you go back one slide, analyze the match there. So exposure in this case is purely whether they took estrogen or not.
Right.
And the control is those without uterine cancer.
Right. So this group here is all your controls. They're women without uterine cancer. These are all your cases. And then everyone inside here is either an estrogen user or a non-user. Yes?
So the way this is usually referred to in like the literature, it just says that they're matched for something. So in these cases, this is matching for estrogen use.
No, I don't know what they were matched for. The exposure is estrogen use. So they might have been matched for a number of years since menopause or something like that. And this analysis is used when you do that design where I said one case comes in and then you get another case that matches them in terms of if it was, like, it's not going to be gender. So if it was age, years from menopause, or, you know, race. something like that. So you have those three. So you have your case come in, then you're looking for a control that matches them in terms of, you know, age, time since menopause, and ethnicity. And then you're going to match them, and they're considered a pair. That is totally different than if I had group matching, where I say, okay, for every 5 people that I have in the age range 40 to 50, I'm going to have another 5 people, but I'm not doing one-on-one matching. Then you can analyze it normally. But whenever you match people one-on-one, you have to treat them as a matched pair. You normally are not doing this by hand. A computer program is doing it, but you want to use a match of analysis if you have matched people one-to-one. Okay. So in this case, this is the odds of low birth weight with controls or cases. They wanted to know whether brain tumors in children were associated with a higher birth weight. And so they went about doing this matched analysis. And again, here you have your controls, and it's whether they were high birth weight or not high, but you know, above 8 pounds, which is normal weight, or less than 8 pounds. And then they had the cases with the same definition. So remember that when we do this, we don't care at all about these white boxes because they're what we call the concordant pairs. They are both exposed, both unexposed. What we care about are these, the discordant cases. Our odds ratio is going to be, what is this formula? B over C, and so in this case, B over C is equal to 2.57. And then here we have a smoking, and we're looking at sudden death. And so we have whether or not the people were cases, they had sudden death, whether they were controls, and then we looked at smoking, more than a pack a day or less than a pack a day. So if we were going to do a matched pairs analysis, can someone tell me what the answer would be for the odds ratio for this table? (36/8), is that what I heard? That's correct. So that's B over C. So that's simply what you're doing for the matched analysis. Now they want you to use the data from the above table, unmatch the pairs, and then calculate the odds ratio. So if you unmatch the pairs, you now have your regular fourfold table, and so you're going to have exposed or not exposed, and then you're going to have your cases and your controls. So can anyone tell me what would go into this box? How many cases were exposed or smoked more than a pack a day? How many cases were exposed and smoked more than a pack a day?
Oh no, 34.
Wow, we got a lot of different answers. So go all the way across. So 38, right? It's cases. Everyone here is a case, and all of these people smoked. So it's the sum of them. It's going to be the 38. So this becomes 38. And can anyone tell me what this box is going to be on that side? The exposed controls? 10, right. It's everyone who smoked in this control group. So this is going to be 10. And then what do we have over here? 42. And this is 70. So if we do it this way with the regular odds ratio, what is it going to be? So what's our formula? So AD over BC. So what is the formula? So it's 38 times 70, and we're dividing that whole thing by 10 times 42. And this equals 6.3. So does everyone see where the numbers came from? You know, I think, again, if you just go home and go over it, it should make a little more sense. But the important thing here is that if we did the matched pairs analysis, so whatever we were matching on in this case, we got an odds ratio of 4.5. When we did the unmatched, it was 6.3. So that's kind of confounded, or we're adding in the effect of whatever we matched by. We're not any longer controlling for it by doing it this way, and that's why it's a little higher. Because it's not only the effects of smoking, it's also whatever we had matched on, we're no longer controlling for when we do it this way. And that's why we do a matched analysis, is to control for something. All right, so why don't we take a 10-minute break? Yes, sorry.
When do you do the matched analysis versus unmatched?
Whenever you recruit people into your study as a matched study. So if you have Mrs. Smith who's 80 years old and, is white, then you want to match her to someone else. So when a control comes in that's 80 years old and white, that's going to be her matching control. So you always kind of treat them as a unit. And that will control for both their age as well as for their ethnicity. And that's what the matching does. It takes out those two variables because you're doing like one-on-one, you're making them into a pair. And that gets rid of those two factors, whatever you match on. Anything else? Okay, so get up, stretch, and we'll be back at 4:30. Hi.
The first example you showed of the matching.
Okay.
The question in what is the estimated relative risk? Is that just like something that you run in the test and expect us to know if it's actually the relative risk or the odds ratio? Would you just say it the same way?
Yeah, and we'll go through some more examples. So if I say estimated relative risk, we're thinking that it's going to be an estimated relative risk is like an odds ratio, because it's a case control study, so that's what we're calculating, an odds ratio. But because if it's rare and things, we think it might kind of represent a relative risk.
So would it be wrong? So it'd be wrong for you to ask in that question, what is the relative risk? You might say estimated relative risk.
Right, exactly.
All right, thank you.
Okay.
Question about our definition of an odds ratio. You said when it averages greater than 0, that means that the first factor is super exposed. But when it's less than 1, they're exposed.
So in other words, they're less likely to have been exposed.
What would be the correct calculation to say that like greater than 0 would be like really what was the correct factor?
I shouldn't use the word factor really, because if you're risk factor makes it sound like you're doing a relative risk and you're not. And so protective factor, I was trying to come up with a term that wasn't risk, protective risk factor, so I took out the term risk, so maybe it would be less confusing, but I see why you're confused. It should really just be that they're less likely to have been exposed. Okay.
Heard it.
Okay.
I don't know if I was one of the 5 people that you mentioned who did submit a thing. I stuck in Dropbox this morning. I also sent a thing this morning, but
I don't remember getting an email. I think I saw stuff in the box. What was
really?
the paper copy?
It was autism and disease.
Yeah, I didn't get that.
You didn't get the.
No.
Oh, okay.
And I'm a little concerned about that because it's not really efficient.
Oh, well, I was thinking, like the celiac disease aspect is, but I mean, if you want to do, and the thing is, like, one of my friends is, like, really concerned with that, so I was like, and I did a lot of, like, celiac disease.
So are you more interested in celiac disease or more interested in autism?
Celiac disease.
All right, so then there's a lot of stuff out there with the nutrient and
Right.
celiac disease, so just go back to that and try and find that.
Okay, but you didn't get the email, which is strange. Okay.
Unless your definition of morning is after 11, because I had to leave it,
Yes.
be in the car at 11 and drive here for a 12 o'clock
Okay,
appointment.
alright, so that's probably why. But I'll that's
Yeah, so just fix that, okay? Hi.
I have a question about odds ratio.
Okay.
So you said that with that example, that cases were 1.6 times as likely to be exposed.
That exposed to smoke, right.
Can you also say that smokers are 1.6 times as likely to be cases?
You kind of can, but you have to be careful. You're treading a line there when you're kind of talking about it as increased risk.
As if it's a risk. Okay, that's my question. On one of your slides, it has like both the definitions. So the second definition is like you qualify if the cases were similar, representative of all cases, if the controls represent the population.
Control studies aren't done
historically not. I saw them being used differently, but now I understand. And then also, you said this, but I just want to make sure. We can calculate odds ratio and relative risk using the cross product multiplication.
No, odds ratio.
Only odds ratio.
Only odds ratio. You can't do it.
Oh, that way.
Right. Relative risk is always the incidence, so it's going to be the number.
Incidence of exposed, incidence over non-exposed.
Right.
Okay, and then my last question was, studies, is it always moved data? Because I saw one of the slides that said like meat, it was like meat consumption of women in different countries.
Yeah, but that was still based on disappearance data. It was based on that country's breast cancer rates and countries what they call disappearance data. So in other words, we have this much cattle in the country.
Okay.
Now we only have this much, so we must eat that much and export that much. So it's really based on the
Like a group data, like the grain example, like the quality.
Same thing.
But of course there could be issues with grain being used
for
for
the
cattle.
for the cow, right? And that's why it's a problem. We didn't even say that it was eaten by pigs.
Yeah.
And that's why there's issues.
Okay, I was confused. I thought it was secondary it's the status. Right. Okay. All right. Thank you.
And trying to understand how those fit in the original book. So, like here it's obvious, if the case is exposed, it goes here. And then that is a little less obvious. I know if you like only look going across, it kind of makes sense, but
Okay, so here you have, so just think of it that these are cases and all of these are exposed.
so you like ignore this.
Right.
Sort of like all these things.
Right.
Yeah.
And that's where the
Yeah,
38
a few of
comes
us are
from.
talking about it, so I don't know maybe.
Okay, so it's just, kind of ignore what's up here and say, okay, out of the cases, how many of them smoked? It was all of these 38. And how many didn't smoke? It was all of these 42. So now when you have your cases, it's your 38 exposed, 42 non-exposed.
Right. I get how to put it in the box, but I don't get how would you make this table on your own, or it's impossible to do.
Oh, you wouldn't be able to, except for like with the example that I had with the estrogen. We put that in our own because we had this. So you need one or the other.
Okay.
You can't just make up the numbers. So by looking at this, this is a discordant. This is a woman with uterine cancer and a woman with used estrogen and one without that didn't use it. And so you figure out which of these 4 boxes they go into, and you could just do like
So this is number of people.
number of pairs that fall into that. Because it's a
why then you
control
have
that's
to add
exposed and a
it.
case that's exposed.
Thank you.
Okay.
Two questions. Okay, I have a question from the second lecture. Is that okay? On the slides, it looks like the mortality rate and the treatment rate are the same thing. I'm like confused.
The mortality rate is the same as the pre-death rate.
Oh, it is?
Yeah, but then because mortality rates, we're going to adjust it for something like at least for 8. And we'll talk about that when we get into compounding. But it's really the same thing. When we use this term food, it just means that it's not adjusted for that. So it's simply the number of people that died divided by the midpoint population,
But then mortality rate could be like,
age adjusted.
okay.
And then you'll see, like when we get into the compounding lecture, how that really changes.
Alright, that makes sense. And then, I know these are questions, but I just wanted to ask,
I don't know yet because I have to find out how many people. I think there's 2 of you, so I need to find out how many people available and how many I know
okay.
are going to have to take it, and then tell me what the right
Okay,
answer
yeah,
is.
that's fine. I just wanted to.
It'll be sometime between Monday and Wednesday.
That's fine. Thank you.
All right. If you guys could go back to your seats. So from what I understand, there was just a little bit of confusion here with this. When you want to figure out where these numbers are coming from to get onto the four-fold table on the board, just pretend this top part doesn't exist. So you're looking at the cases and you're looking at how many smoked, and you come out here to the 38. So just kind of, I don't know how to do it, but cover this up with your hand and then just go across here. There were 38 cases that smoked. Go across here, there were 42 cases that did not smoke, and that's how that gets into the table. And likewise, you just cover this all up and say, okay, out of the controls, how many of them smoked? 10. How many didn't smoke? 70. So that's how you think about putting those into the table. So now we're moving on to a cohort study. So they are either exposed or not exposed, but remember here they're self-selecting. So you start out with the population. This is a cohort. They start out without disease because you're going to look for risk for the disease. So you want everyone without the disease to begin with. And then they're either exposed or not exposed. You follow them over time and see whether or not they develop disease based on if they were exposed or not exposed. This can be done either as a prospective cohort study where you assemble the cohort today, follow them forward in time, all the follow-up occurs in the future. Or you can assemble a cohort in the past. But remember, this is something that has to be based on existing records. You need to have, like the examples I gave, old school records from when they were in elementary school, and then follow that whole group forward from the elementary school of 1948 until today and see who got disease and who didn't based on whatever was recorded back then. But everything has to be recorded then. It's data that was collected before they got disease. That's why it's like a cohort study. But all of that follow-up has already taken place. So when you have a cohort study, you're going to start with people who are exposed or unexposed. They get disease or they don't. And so they drop into the four-fold table like this. And then what you calculate is the incidence in the exposed divided by the incidence in the non-exposed. And that would be your relative risk or your rate ratio. And that, what would this be used for? What risk, when do you calculate this? What type of study designs? Cohort? And a randomized controlled trial. So for both of those, we do this exactly the same way. It's just the only thing that's different is the exposure or the non-exposure was forced upon them. It wasn't something that was self-selected. So here is an example of 3,000 smokers, 5,000 non-smokers. They were followed forward to see who would develop coronary heart disease. So we can get the incidence among the smokers. It's 84 per 3,000 or 28 per 1,000. Incidence among non-smokers, it's 87 per 5,000 or 17.4 per 1,000. So if we wanted to calculate a relative risk for this, what would we use? The relative risk for smoking and developing coronary heart disease. What numbers from here would you use? Right, so 28 divided by 17.4. So that's going to be about 1.6. And that would be your rate ratio or your relative risk. They're kind of interchangeable, the terms. So everyone see where you get the calculations there? Yes?
So you're saying the difference between a cohort study and a randomized controlled trial is that the exposures chosen in the cohort study and like forced on the subjects in the randomized controlled trial? In a lot of randomized controlled trials we've been looking at, there's like the issue of adherence and crossover and treat and all that stuff. Do people ever intentionally do cohort studies to get around that issue because they're choosing their own exposure, no one's
A cohort study usually is not more useful than the randomized controlled trial simply because of those table 1 differences that I tried to stress today and during the cohort study. When you have a cohort study, not only that behavior that you're talking about is different, but many other things are. When you do the randomized controlled trial, like the 2 papers we reviewed at the beginning of class, that table 1 shows that there's, no differences anymore between the populations. So it wouldn't be preferable to do a cohort study over a randomized control study because of that. The only reason why you might look at it in a cohort study is the cost of a randomized control trial. Is it a little more intensive with the subjects, and you'd want to at least have some kind of a proof from an existing cohort study before you went on and did that. Anything else? Okay, so here is for a randomized controlled trial. Same as the cohort, you're starting with a sample from the population, but you're randomizing to the intervention so that they're either treated or the control group, and then you're following them to see who got the outcome. So for both cohort and randomized controlled studies, the measures of association is the relative risk, which is a direct measure of the association between the exposure and the outcome. It's the ratio of the incidence of the disease in the exposed group to the incidence in the non-exposed group. So just like we calculated with the smoking and put in terms of a formula, it's just listed here. Incidence rate in the exposed, or in the case of a randomized controlled trial, the treated group, divided by incidence rate in the non-exposed, or in a randomized controlled trial, the placebo group. And that's how we calculate that. And many times when you read a paper, you're going to just see something like this, which will show the relative risk. The circle represents the point estimate, what was the exact relative risk. And then these are the upper and lower confidence intervals, usually a 95% confidence interval. So if you have the circle or the point estimate to the right of here, it means that it's a risk factor. If it's to the left, it means it's protective. And remember that if any of these lines cross over the axis here, it means it's not significant, because it means that one is included in the confidence interval. We talked about cumulative incidence. It's the proportion of people who develop the disease over the follow-up period of the study, or the average probability that an individual in the cohort will develop the disease over the follow-up period. So here the numerator are all incident or new cases of the disease over the follow-up period. And the denominator, importantly, is all the people that are at risk of the disease at baseline. And so in most cohort studies or randomized controlled trials, this is going to be everyone in the trial, because normally we exclude people that already have the disease from these trials so that they would not be part of the denominator. And we talked a little bit about that this is not the best thing to calculate if a lot of people are lost to follow-up. And I gave you some more advanced statistics that you would use instead, like the product limit estimate and the Cox proportional hazards. I don't expect you to know that for the exam. That was simply so that you would have a better understanding of how we do this. So here's an example of the cumulative incidence. So if I asked you what was the cumulative incidence from this graphic, what would the answer be? Yeah. Go ahead. Just 2? 2 over 8? Just 2 over 8? No, it's 2 over 8, but it's over 2 years of follow-up. Don't forget to specify the time frame that you're talking about. Because you could say 2 out of 8 over 1 year if you just stopped it here. Yes?
Can you do 2 over 14 people years, though? Person years?
Well, if you were not doing cumulative incidence, if we were doing incidence rate. So remember, those are 2 different things. So here the cumulative incidence is simply how many people got the disease divided by how many people are in the study, and you have to specify the time frame. When we take it a step further, which you already wanted to do, that's the incidence rate. And so that's the calculation of the true rate of the disease. So the numerator is all incident cases of the disease over the follow-up period, and the denominator here is that concept of the person time, or the sum of all the time that everyone has contributed as a study subject while still at risk for the disease. If they get the disease, we actually stop calculating their person time. So now, what is the incidence rate in this example?
2 over 12.
It's 2. But it's 14 because you have to count the 1 year until each of these got the disease. So it's 2 over 14 years of person time. You should understand how to interpret the relative risk of a disease. It's the risk in the, if it's equal to 1, you're basically saying the risk in the exposed is equal to the risk in the non-exposed, or there's no association. If the relative risk is greater than 1, the risk in the exposed has a greater risk in the non-exposed, so it's a positive association. Or you can have it less than 1, where the risk in the exposed is less than in the non-exposed. And this might indicate a protective relationship. So there are absolute and relative measures. Absolute measures would just be like the incidence rate of the disease. And then you also have the relative measures. So the incidence rate tells us how many people will get the disease if the exposure is removed, because, or we can just know how many we have to plan for, how many cases of disease do we have. But when we want to talk about the association between two variables, that's when we need the relative measures, like the relative risk, because they're looking at how strong is the association, say, between smoking and lung cancer, or between smoking and coronary heart disease, some of the examples we've done. So if you look at this example here, does the relative risk change with each serum cholesterol level in men? As you go from low to high serum cholesterol, and in men, which is these two left things, do you get more risk with higher cholesterol?
Yes.
Right, it's true for either age group, right, the young or the old. How about in women? Do you see the same increase in risk with serum cholesterol as you did with the men? No, you don't, right? Because it's kind of flat, and maybe in the older women you might see more of a trend towards it, but it's not really clear-cut. So these are the relative risks. This is talking about how strong is the association between serum cholesterol levels and the risk of coronary heart disease. These are giving us the incidence rates in these different populations, so we can have an idea of what kind of disease rates we can expect in each group. And this is just shown graphically here, where you can get an idea of the relative risk. Remember how to read something like this. You have the low cholesterol and the high cholesterol by different colors, and this is in smokers, and this is in non-smokers, and this is in smokers. So you can think of smoking as adding to the effect of what you get from the cholesterol, because in high cholesterol, if you're a non-smoker, you're here. If you're a smoker, it's all the way up here in terms of the relative risk. So the measure of association, whether it's a cohort study, is going to, here for this example, it's a cohort study. We're looking at the relative risk. So we have the exposure status. They were exposed. They got disease. And so we divide that by the total for the incidence rate in the exposed group. We get the incidence rate in the non-exposed group. So when we're doing the relative risk, it's simply the ratio of those two numbers. There's another term that I want you to be familiar with, which is the attributable risk. And that's the difference in the incidence rate, subtracting out the incidence rate in the non-exposed from the incidence rate in the exposed. And we're going to go through several examples of how to calculate this. So here is the two ways of calculating risk. You can have the difference in the incidence rates or a ratio of incidence rates. So which one would you use for an association? Yeah. Right, the ratio of the incidence rates is how you, that's the relative risk or whatever. That gives you an idea of the association. So in population A or population B, where is there a stronger association between the exposure and the disease? Right, and population A, because it's 4. Which population has more excess risk? Population A or population B?
Population A,
Why?
because it's 40 divided by 130 versus population B, where less.
How do we calculate excess risk? The extra risk. It's that attributable risk formula. Is the same as excess risk. So if you look here for the excess risk, where is there more excess risk? Population A or population B? They're the same. They're both 30, right? So the excess risk, there is no difference. They're exactly the same in these populations. So this is just graphically showing us that you can calculate the incidence in the exposed, the incidence in the non-exposed. If you are interested in whether an exposure relates to the disease, that's going to be this here. But you always want to get rid of the background incidence, and that's why you kind of have this non-exposed group, so you can get rid of that. So remember, your incidence in the exposed group is not all the cases you get. It's all the cases you get in addition to the number of cases you got from the controls. So it's an additional group here. So you may want to know here, say, what are all the deaths that are caused by smoking? Well, these are smokers, these are non-smokers, but there's a certain background risk in the non-smokers, and you want to subtract that out to get to this smoking effect solely, just to separate that out from all of the effect of the disease. So this is just shown in a different way here. You have the level of risk in exposed and the non-exposed. So in the exposed group, there's going to be a background risk that you can get from the non-exposed group. And then all this additional darker blue part is what we're thinking of as the incidence that's strictly due to the exposure, as shown graphically here. So here are some calculations of attributable risk that you can do for the absolute incidence or the proportions. So in the exposed group, you can have the incidence in the exposed group minus the incidence in the non-exposed group, or the proportion of incidence that's attributable to the exposure. So you're just kind of making that a percent or a proportion. So it's the difference in the exposure between the exposed and the difference in the incidence between the exposed and non-exposed, and then divided by the incidence in the exposed group. I think what I'm going to do for now, just to make sure we get through everything, is I am not going to worry about in the total population. I'm going to skip these parts. I will not test you on that because I'm worried we won't have enough time to get through if I keep up with that. So don't worry about the total population. So here is an example for smoking. So here you're looking at lung cancer and coronary heart disease mortality in male physicians based on if they were smokers or not. So how strong is the association between lung cancer and smoking? Someone say something over there?
92%. Like it's a strong association.
Well, the strength of the association, what term do we use to see how strongly two variables are related? Yeah. Right, the relative risk. So how strong is the relative risk for lung cancer and smoking? It's very strong. It's 14, right? That's the number. It's 14. In the lung cancer cases, how much of the risk of lung cancer is due to smoking? So that's this concept of attributable risk. So you simply take how much of the lung cancer deaths were in the smokers, subtract out the background part from the non-smokers, and we get the attributable risk. Remember, that's just the simple subtraction. Or we can do it as a proportion. And that was what you had talked about before. The proportion that's due to smoking is this 130 divided by the 140. And that's the 92.9. So what this illustrates is two things. So if you look at lung cancer and smoking versus coronary heart disease and smoking, the relative risk is much stronger with the lung cancer. We have a relative risk of 14 and only 1.6 with coronary heart disease. But when we look at the attributable risk, look at the big difference here. It's almost twice as high in the coronary heart disease. And that is because there are so many more cases there. So whereas the association is a little bit weaker, because the disease occurs so frequently, you get more cases that are attributable to that. Okay? So this is just a smoking example, looking at it somewhat differently. Again, lung cancer, coronary heart disease. So here we can have the relative risk. Here is 3 for both of them. So the association between smoking and lung cancer is 3. The relative risk for coronary heart disease and smoking is 3. But you can see that there is a difference in the attributable risk. And this, again, is because there are so many more cases of coronary heart disease occurring than there are of lung cancer that you get a greater number of attributable risk. So just understand that the attributable risk is somewhat related to how many cases you actually have of that disease, because you're subtracting out the number of cases without exposure from the number that were exposed. So this is the incidence or the absolute risk per thousand in non-smokers. In smokers, you have the relative risk and the attributable risk here. So how did they get this relative risk here? What 2 numbers did they use? Right, so they took 29.7, divided it by 7.4. So the incidence in the exposed divided by the incidence in the unexposed. And how do you get the attributable risk? What do you do with these numbers? You subtract it out. So the incidence in the smokers minus the incidence in the non-smokers. And that's how you get this. So just understand how you can calculate the attributable risk, how you can calculate the relative risk, and these numbers here are just the absolute risk. Okay. Okay, so let's just go through one example. This is the one we had seen before. We had 3,000 cigarette smokers and 5,000 non-smokers. 84 people developed coronary heart disease in the smokers, 87 in the non-smokers. So remember, we had calculated the incidence was 28 per thousand and 17.4 per thousand. So if we want to look at the attributable risk, you can do the incidence in the exposed minus the incidence in the non-exposed. So you get 10.6 per thousand cases of coronary heart disease. So if you get people to stop smoking, you can stop about 10.6 per thousand cases of coronary heart disease from occurring. Or if you look at the proportion here, we're just adding in, dividing by the incidence in the exposed group, that 28. And there you get a proportion. So here, if you look at the proportion, 37% of the mortality from coronary heart disease among smokers is attributable to smoking. So it's telling you you can get rid of a certain percent of the cases of coronary heart disease just by getting people to stop smoking. And that's where this becomes important for public health. So this next slide is actually talking about how we calculate it in the total population, and I'm not going to ask you how to do this, so I won't go through it. You can review it on your own if you want, but I do want you to understand the bottom line that you can attribute a certain amount of disease to smoking, and if you could get a program to get rid of that, say if these were all based on New York City, then we would hope that we could reduce the coronary heart disease by about 21% by doing quit smoking programs that people actually participated in. So again, just the formulas so that you can be used to it. The absolute risk, the incidence of a disease in a group. So it's the number of new cases divided by the number of people in the group. So that'll be one number for the exposed, one number for the unexposed. Attributable risk is also called the risk difference. So it's the incidence in the exposed minus the incidence in the unexposed. And the relative risk, how many times more likely are exposed people to get disease relative to non-exposed, and that is the ratio or the relative risk. So this is just giving an example. If we were looking at the absolute risk of lung cancer in smokers, 0.96 per thousand per year. In non-smokers, it's 0.07 per thousand per year. The total death rate from lung cancer is 0.56 per thousand per year. So if we do the attributable risk, it's going to be 0.96 minus 0.07. So you always have to get rid of that background risk for attributable risk. So it's the difference, the risk difference. And the relative risk is the ratio here. And it would be 13.7 in this example. Okay, so a lot of studies have found that about 85% of cases of lung cancer are due to cigarette smoking. What is this an example of, this measure? What's an example of? Right, it's attributable risk, or B is the answer here. Okay, this is the results of a 10-year cohort study of smoking and coronary heart disease. You had 2,000 healthy smokers, 65 developed coronary heart disease, 4,000 healthy non-smokers, 20 developed coronary heart disease. The incidence of coronary heart disease in smoking, in smokers that can be attributed to smoking is what? What do you first have to do here? Right, and you want to do it with the same denominator. You don't want to confuse things by having a different denominator. So if you wanted to do this, what are the numbers that you would use first of all? For the healthy smokers, what is the incidence rate? Divided by what? Right, 65 divided by 2,000. Make sure you don't do it the group that's non-exposed. And so that is going to be for smokers. And then what is the incidence in the non-smokers? 20 per 4,000, right? So this is non-smokers. So now you want to get this into 1,000. So let's make everything per 1,000, right? So what would the top one be? $32.5, is it? And then this one is 5 per 1,000. Okay? So everyone see what we did here? We just had to make sure that everyone was on the same denominator. So they're all based on per 1,000 now. So what would be the answer for the attributable risk for smoking? Right, 27.5. It's the 32.5 minus 5 per 1,000. So it's 27.5 per 1,000. And then if we wanted to do the proportion, it would be 27.5 divided by what? The 32.5. So the proportion is just doing the same thing. It's the 32.5 minus 5, and then you always divide by the 32.5. And so that answer is going to be 85%. So it's the incidence in the exposed minus the incidence in the not exposed divided by the incidence in the exposed, and that's the proportion of incidence. So everyone clear on how we got these? Okay, so in a cohort study of smoking and lung cancer, the incidence of lung cancer among smokers was found to be 9 per 1,000, and the incidence among non-smokers was 1 per 1,000. From another source, we know that 45, okay, we didn't do this, sorry. We're going to skip this one because we didn't do that calculation. Okay, of 2872 people who had gotten radiation treatment in child because they had an enlarged thymus, 24 people developed cancer of the thyroid, and there was a benign thyroid tumor in 52. There was a comparison group of 5,055 children with no such treatment. During the follow-up period, none of the comparison group developed thyroid cancer, but benign thyroid tumors developed in 6. So can you tell me what kind of a study this is? It's like a retrospective cohort because they put the records together from who got radiation or not in the past. So now we want to get the relative risk for benign tumors. So what is the first number we need? How many new cases of benign tumors did we have in the people with radiation? 52. And what was the denominator? Right, out of 2872. Okay, so that is going to be 0.0181. And then what is the same thing for the group that was not exposed to radiation? 6 cases out of how many? Out of 5055. So this is going to be equal to, I think it's 0.00116869, something like that. So what would we do in order to get the relative risk? Right, you divide them, right? So if you divide these numbers, you end up with something around, I'm not sure if it's 15 or, it's like 15 or 23. So it's a pretty high, it's 15.2. It's page 23. So 15.2 is the answer here. So you understand you get the incidence in the exposed group, incidence in the non-exposed group, divide them, and that gives you your relative risk. Everyone clear on how we did that? Okay. So what is the annual incidence rate per 1,000 of colon cancer if it's diagnosed in 1 person per month with a community of 500 unaffected individuals, assuming that 1 out of every 5 affected individuals die from this condition? So what are they asking us for here? The annual incidence, right? So what is it that you need in order to calculate that? So how many cases are diagnosed in 1 year? 12, right? 1 per month. So it's 12 cases, and out of what population? 12 over 500, or let's make it consistent, so 24 out of 1,000. Everyone understand where those came from? So the answer here is going to be B, or 24 per 1,000. Because remember, they asked for this per 1,000, so it's going to be B, 24. Everyone know how we got that? Okay, and what is the case fatality rate of colon cancer in the community above? Pardon? 1 out of 5, or 20%, right? 1 out of every 5 dies, so that's 20% is the case fatality rate. So here's a cohort study, and we're looking at serum cholesterol level and the occurrence of MI in women. So 500 women with high serum cholesterol levels and 500 without high serum cholesterol levels are followed for 10 years. 40 of the women with high cholesterol levels and 15 of the women with normal levels develop a new MI. So the incidence rate per 1,000 years for a myocardial infarction among women with high serum cholesterol is what? What numbers would you take from the above description? How many women with high cholesterol develop disease? 40. And what's your denominator here? 500. So that's going to be what per 1,000? So it's 80 per 1,000. So that would be D. Okay, and then you do the same thing. The incidence rate for an MI among people with normal serum cholesterol is going to be, what's the number that develop an MI? 15, and our denominator? 500, so we make that 1,000, so it's 30 per 1,000 is going to be the answer for number 5. Okay, so here's a cohort study. It's the same study, okay? So the rate ratio for myocardial infarction is going to be what? What numbers would you use for this? Right, so it's 80 per 1,000 divided by 30 per 1,000, or it's 2.67 is the answer, so C. So it's just the incidence rate in the exposed, the high serum cholesterol, divided by the incidence rate in the non-exposed. And what about the risk difference? How do you calculate that? So we did the relative risk or the rate ratio. How do we calculate the risk difference? Right, 80 per 1,000 minus 30 per 1,000, or 0.08 minus 0.03, and that's going to equal 0.05. You're all clear on how those numbers come about? Okay, so here is a foodborne illness has occurred, and we're looking at the percent of people that got sick among those who ate a food and those who did not eat a certain food. So the 8 people is the exposed, and the did not eat is the non-exposed, is the way that you can think about this. So this is looking at various foods and what was the attack rate. So now we're going on. This is the same information, just in a table with some added things. So now they have the attack rate in the exposed divided by the attack rate in the unexposed, or what would that be equivalent to? Incidence in the exposed divided by incidence in the unexposed. So that's a relative risk. So this number here is showing us how strongly the different foods were associated to getting sick. It's the strength of the association is the relative risk here. So where do we see the strongest association? What food has the greatest relative risk or the strongest association? Egg salad, right? So it's got the highest relative risk. It's 2.7 as compared to all the other ones are lower than 1.5. Now, what food has the greatest excess risk? It's still egg salad, right? So excess risk is just incidence in the exposed minus incidence in the unexposed. So it still is the egg salad. So now let's go on to we had an epidemiology department luncheon, and there were different foods that were served, and people either were ill or they were well, or this was the total that ate the food, and then for those that did not eat the food, they were ill, they were well, or they were the total of people not eating that food. So the attack rate for people who ate pasta salad is going to be what? Right, 10 over 29. I'm trying to find the pasta salad. Okay, so here's the people that were ill, that ate that food, pasta salad, divided by all of the people who ate that food. So the attack rate for pasta salad is 10 over 29, and that's equal to 34%, so that's C. So what was among the persons who ate specific foods, which food had the highest attack rate? How many say potato salad? How many say raspberries? So look, this is 33 out of 37. It's almost everyone, right? This is 16 out of 19. You're right, the math is a little close, but raspberries win. So raspberries. So all you would do, if I asked you which was the food that had the highest attack rate, you just calculate the attack rate for each of these and see which is the highest number. Then they ask you, the risk ratio for eaters compared to non-eaters is lowest for which food? So here what they're saying is, if you look at the attack rate in the people that ate compared to the people that did not eat, what would be the lowest number? So what would you have to do here? You'd have to do the same thing, right? Calculate 11 divided by 25 divided by 26 divided by 37, and you'd get a certain risk ratio here. So you all understand how you would calculate it? So if we go through and we calculate all of this out, it turns out that the ham is the one with the lowest risk ratio, because it's 11 divided by 25 divided by 26 over 37, or 0.62. So again, this is something that you can, take home and calculate and make sure that you feel comfortable with doing it. So do you guys have any questions?